Okay, the new topic that we're on is friction. And the concept that you have learned in the past is that the frictional force is mu times n, where mu is the coefficient of friction between two surfaces. And you may have learned that mu s is the static friction where there is no motion, and uk is the kinetic friction where there is motion. In other words, these are two different numbers, and almost always the static friction is bigger than the kinetic friction, meaning that if you're, for instance, if you're trying to push something across the floor, it's harder to the friction is greater when you first get it moving. Once you get it moving, it slides more easily. So, we have that mu s greater than mu k in most circumstances. So, now the n is the normal force, which is the force perpendicular to the contact surface. So, and it's compressive, right? Because if you have two bodies and they're in contact with one another, then there's going to be a compressive force holding them together. If there's tension force, well, then they can separate. So this is going to be a force perpendicular to the contact surface and toward the body, compression. Now, what you may or may not have learned that this is the maximum. This mu times n is the maximum friction we can get. We may not mobilize all that friction. And that's one of the things we're going to look at when we do this. This friction is a resisting force. In other words, it acts in a direction that opposes the motion. Opposes the motion if it's moving. If it's not moving, it opposes the impending motion. So, in other words, we will have a friction force when we're not moving, and the direction of it is opposite to the impending motion, the way that it wants to move, basically. And the direction is sometimes a little bit tricky. And again, what we're looking at, the maximum friction is mu times n. The maximum we can get is mu times n. And we're going to use our concept of cuts still. We're not violating anything or changing anything that we've done to this point. We're still going to make cuts, but now we're going to make cuts at a frictional surface. And we're going to, we have a rule for that. In the same way that, like I say, when we cut through a pin, we have an X and Y force. When we cut through a roller, we have a Y force. When we cut through a truss member, we have a tension or compression. When we cut through a cable, we have tension. And when we cut through a frictional surface, what do we have? We have a normal force and a frictional force. So, this has both a normal force and a frictional force. So that's what we put. The normal force is perpendicular to the surface and the friction is parallel to the surface. So when we cut through, so we have to remember our rules. We're just going to follow exactly what we've been doing. And now we're going to make cuts through a frictional surface. That's pretty much what we're doing here. The rest is what we've been doing all along. So, okay, let's start out with the basic example, which is that we have a block is being pulled with 60 pounds, but it is not moving. The properties are given. We've got our μs and our μk, and what we want to do is find the frictional resistance mobilized. And then I'm going to introduce this factor of safety against sliding, and that factor of safety, which is not a theory, it is a definition that is imposed by practitioners to determine the amount of safety we have. And it's a little bit nebulous term. I'm just not going to kid you about it. And it's defined in many different ways in practice. I'm going to show you one way that it's defined. Like I say, there's no theory behind it. We just introduce this as a way to make sure that we don't design our systems to be, just barely better than what we need. We need to have extra safety in practical designs, because things in real life are unpredictable, and we don't necessarily know all the properties perfectly, and we don't know all the loads perfectly, so we always throw in some safety. So in this particular case, we want to know if we're worried about this sliding. For instance, suppose this is our situation, and we don't want this sliding across the floor. Well, how much safety do we have against sliding? That's going to help us. Maybe we have to reduce this load. Maybe, maybe we need to increase this weight, or something needs to be done, or maybe, something has to be corrected. And if we figure out what we call a factor of safety, that's going to give us an idea whether or not, we have sufficient safety reserved to make it much less likely that this is going to slide across the surface there. And so the way that we're defining it in this case is we're going to take the F, the frictional force at initial sliding, F is the frictional force, divided by the frictional force that we have, the frictional force that we have mobilized, that's there right now. So we call it mobilized, that's what's there. How much okay, so we make our free body diagram here. We come in here, we make our cut at the frictional surface, and we have our weight, which is the 200 pounds. We have the 60 pounds we're pulling it with, and then what do we do at the frictional surface? Well, we have an N and an F. And we know that it is not moving, so that means everything we've done previously works, which is the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. We'll do the sum of the forces in the y direction first, and this is a very easy problem. So what do we have? We got the n. So I look at this the way we always do. N minus 200 equals 0. So we can solve for n. N is 200. And then we take the sum of the forces in the x direction equals 0. As I said, this is reasonably straightforward. But I look at my picture, that's 60 positive, and that's also F positive, because they're both going in the positive x direction. So I have 60 plus F equals 0, which means what? That F is equal to negative 60 pounds. And when we draw our final free body diagram, it looks like this. We find that the friction that exists, or the friction we're mobilizing, is 60 pounds. And that's this number right here. And so this is our free body diagram. It's in equilibrium. Now, we've been told it's not moving. What would it take to get this moving? Well, to get it moving, we know the static coefficient of friction is 0.38. So we can figure out what frictional resistance there is to initial sliding, so it's going to be 0.38 times the N, the 200 there. Notice it's not this 200, it's this 200 right here. It's the N. The N is very clearly, so don't get confused. It's that N right there, not the weight here. I mean, they happen to be the same in this case, but when we start looking at other problems, it's not going to be the same. So 0.38 times the 200, the 0.38 comes from there, gives us 76 pounds. So if I look at this, and so then I have my frictional, so I put down my F max. And that is the 76 pounds, and then what do? Now I look and I solve for P, taking the sum of the forces in the x direction equals 0, and I get that P is equal to 76 pounds. So I have my factor of safety using this definition. Well, F at initial sliding is 76 pounds. And what we've mobilized, what is actually there is only 60 pounds, so I have a factor of safety of 1.27. That may be sufficient, but the way that it works in practice is you will have a defined factor of safety that you need. Maybe it's 1.25, maybe it's 1.5, maybe it's 2. It depends on the whole situation. And then you decide whether or not this value is sufficient safety for your situation. I'm not going to define what that needs to be right now, but that is our factor of safety in this particular